Okay, so in this video, we're going to be going over the 2002 AP Calculus exam. I totally didn't just record this question and then have the file corrupt on me, so with that, good luck. Let's get started. Nice. Okay, so we have f and g be functions that are f of x e to the x, and g of x is the natural log of x. And then I've gone on Desmos and gotten sketches of these two functions to help me and you. If this is your actual test, you could have just gone on your graphing calculator and done this in about a minute. So we're good. So in part A, we need to find the area of the region enclosed by the graphs of f and g between x equals 1/2 and x equals 1. So I'm going to start labeling x equals 1/2 here and x equals 1 here, like that. Alright, so now that I have that, I can sketch the region that I'm talking about, like so. And I think drawing sketch is really important because it helps you visualize what it is you're doing, and especially in this unit where it's very conceptual, this sketch can be really helpful. Okay, so to find the area, now that we've already defined our boundaries here, we can look at that. We can look at the bounds of integration, and since we're going from x equals 1/2 to x equals 1, 1/2 and 1 are going to be the bounds of integration. And then also notice that e to the x is the top function, and the natural log of x is the bottom function. When we're dealing with multiple functions here, you'll either have a top and bottom function or a left and right function. So it's important to make that distinction to be able to properly execute the integral. So we're going to be integrating from, well, we're going from 1/2 to 1. So 1/2 to 1. And then what you're going to put here is you're going to put your top function minus the bottom function. That's the formula. And then in our case, the top function is e to the x, the bottom function is the natural log of x, so I can replace all this stuff with e to the x, my top function, minus the natural log of x, my bottom function, and this comes out to be, in the calculator, 1.223. Okay, that's your final answer. You get 1 point for the correct integral and 1 point for the correct final answer. Alright, part B. Find the volume of the solid generated when the region enclosed by the graphs of f and g between x equals 1/2 and x equals 1 is revolved around the line y equals 4. Okay, y equals 4 is this horizontal line all the way up there. And then since we're dealing with two separate curves here, we're going to have two different distances from the axis of rotation, right? We're going to have the distance from the axis of rotation to this curve and the distance from the axis of rotation to this bottom curve. So that means we need to establish two different radii. The first radii is going to be going from y equals 4 to this red curve. So it's going to be, I just imagine this is 4, it's really not, but whatever. It's going to be going from here to here, right? And the second curve, the second radius is going to be going from here to the bottom curve down here. I'll call this one little r, and I'll call this one big R. And then now to numerically find values for those, our little r, so notice that the whole distance here is 4, but we're only interested in this distance. So it's going to be 4, the total distance, minus this chunk here. And what is this? What is this height? Well, it's e to the x, right? So we're going to take the entire distance of 4, subtract this e to the x, and then this leftover part is our radius. So the radius is going to be 4 minus e to the x. 4 is the total, e to the x is this height. The same logic for the big radius is going to be 4. And then for the deciding whether it's plus or minus, an important thing to notice here is that the radius, the big radius, is going to be bigger than 4 because it's going from 4 to 0 and then from 0 to this extra bit. And then since natural log is negative from, well, for values that are less than 1, for x values that are less than 1, the natural log is negative from 0.5 to 1. So since we want this to be greater than 4, we're going to subtract the natural log of x, because it's going to be 4 minus a negative number, so it's going to make this bigger than 4. Now that we found the radii, we can use the formula, which is the integral from a to b, where again a and b are 0.5 and 1, of big R squared minus little r squared dx, and this whole thing is being multiplied by pi. So let's plug in some numbers here. We have pi times the integral from 0.5 to 1 of big R squared, so 4 minus ln x squared minus little r squared, 4 minus e to the x squared dx. And then when this whole thing goes in the calculator, we are going to get an answer of 7.515 pi. And for points, you get 1 point for including the correct limits and the pi, 2 points for the stuff in here, 1 point for the final answer. Alright, so part C, let h be the function given by h of x is f of x minus g of x. Find the absolute minimum and absolute maximum value of h of x, on the closed interval 1/2 to 1. Show the analysis that leads to your answers. Alright, so when we're thinking of absolute minimum and absolute maximum, the first thing that should come to your mind is critical numbers and endpoints. Because when you're trying to find absolute extrema, they can only be in one of two places. First of all, they can be at your endpoints. And then 2, they can be at your critical numbers. So what are our endpoints? Our endpoints are 1/2 and 1, right? Because we want to find the extrema on those 2 points. So 1/2 and 1. Actually, let me specify here a little bit better. I'll say x equals 1/2 and x equals 1. And then for our critical numbers, well, let's see here. We have the function f of x, h of x, being f of x minus g of x. And to find the critical numbers, we're going to have to take the derivative of h and set it equal to 0, right? So h prime of x is therefore going to be f prime of x minus g prime of x, right? What is f prime of x and what is g prime of x? Well, f of x is e to the x, so f prime of x is going to be e to the x. And then g of x is the natural log of x, so g prime of x is 1 over x. Therefore, I can say my h of x is e to the x minus the natural log of x, and then h prime of x is e to the x minus 1 over x, right? This is important. I'm just gonna do that. Alright, so now that we found h prime of x, we're gonna set it equal to 0. Important, do this on a separate line. So e to the x minus 1 over x equals 0. Put this in your calculator in your graphing mode, and then you're going to get out that x is equal to approximately 0.567. Okay, so now that we have a critical number, the only critical number on the interval that we want is x is 0.567. Now that we have our endpoints and our critical numbers, the fastest way to do this and the most neat is to set up a table. So what the table is going to look like is we're going to have x and we're going to have h of x. And on this x side, we're going to put the critical numbers and the endpoints. So we'll put 1/2, 1, and 0.567. Endpoints, critical numbers. And then to find h of those values, remember how I said up here that h of x is e to the x minus the natural log of x? Well, I can just take these x values, plug them into h of x, and I will get, so for x equals 1/2, I'll get 2.342. For x equals 1, I'll get 2.718. And then for x equals 0.567, I'll get 2.330. And now these are the only places where the absolute extrema could be. And then so the highest one here, 2.718, that's the absolute maximum. And this lowest one, 2.330, is the absolute minimum. And now let's be really careful here and look at the wording. So they said find the absolute minimum value and the absolute maximum value. They didn't say x value, they just said value. So when they say value here, that means they're talking about y value. If they wanted you to find the x value, they'd explicitly state find the x value where the absolute minimum or absolute maximum occurs. But since they didn't say that, we want the y values. So in your explanation, you'd say the absolute minimum is 2.330 and the absolute maximum is 2.718. Okay, so for your points, you'd get 1 point for taking the derivative and setting it equal to 0, another point for this kind of a setup to show that, to find like h of x at each of these possible values, and then 1 point for correctly identifying the minimum and maximum, the absolute extrema. Okay, with that completed, let's move on to question 2. Alright, we're doing question number 2. As you can see, there's a lot of words, so I had to make the font size smaller. Hopefully it doesn't make that much of a difference, but we'll see, Alright, so we have the rate at which people enter an amusement park given by E, the function there, and the rate at which people leave given by L, the function there. E and L are measured in people per hour, and T is measured in hours after midnight. The functions are valid for T between 9 and 23, which are when the park is open. At T equals 9, there are no people in the park. Alright, part A. How many people have entered the park by 5 p.m.? T is 17. So we're starting at T equals 9, and we're going to T equals 17, and we want to find the total number of people who have entered the park in total, right? So that means we're going to be doing an integral to find the total area under a curve. And since we're talking about how many people have entered the park, that means we're going to be integrating the top function here, E of t, which is how many people are entering the park at a certain time. So that means we're going to be integrating, and since we're starting at the opening time, t equals 9, and going until 5 p.m., t equals 17, we'll have that. And then the function we're going to be integrating is E of t, like that, and stick a dt on the end, have this, plug it into there, put it in your calculator, and we are going to get 6,004 people. It should be pretty intuitive why the units are people, because we want to find out how many people have entered the park. Okay, and this is a 3-point question, 1 part for the bounds, 1 part for the integrand, and 1 part for the final answer. Alright, part B. So the price of admission to the park is $15 until 5 p.m. After 5 p.m., the price of admission is $11. How many dollars are collected on the given day? Okay, so let's think about this. Until 5 p.m., oops, I'm still on eraser. So until 5 p.m., the number of people who have entered is the integral from 9 to 17, right, of E of t that we just did. That's how many people entered the park until 5 p.m., from the opening time until 5 p.m. From opening to 5 p.m. And then after 5 p.m., the number of people are going to be the integral from 17 to the closing time, where the closing time is t equals 23. And this is still going to be E of t. So this is the total number of people who entered from opening to 5 p.m. This is the total number of people who entered from 5 to closing. Alright, so this is the total number of people, and then for each person, it was, how much was it? It was $15. So if we take the total number of people and multiply it by 15, that'll tell us how much money they collected from this group of people. So that's going to be 15 times the integral from 9 to 17 of E of t. And then, so for this group of people, the admission cost was $11. So we'll take this total number and multiply it by 11, plus 11 times this integral from 17 to 23, E of t. And then this is going to be a straight calculator question, and we're going to get $1,04048. And if you look at the question, they asked how many dollars were collected, so the units are dollars. Okay, now let's look at the next part. Oh, I quickly forgot to mention, the points for this. You get 1 point for setting up the question. Interestingly enough, you don't get any points for the right answer. So yeah, there's that. Anyways, now let's move on to the next part. We have h of t being this function here, the integral from 9 to t of e of x minus L of x for 9 to 23. So let's think about what h of t represents here. We have e of x here being the people who entered, L of x being the people who left, and then we're taking that value in terms of x and we're integrating it from 9 to t. So if we take the number of people who entered minus the number of people who left, and we take that number and we integrate it from the time the park opened to a certain time t, that's going to give us the amount of people in the park at a certain value of t. So if we plug in, say for example, 10 for t, h of 10 is the integral from 9 to 10 of e of x minus L of x. That's going to be how many people are in the park at t equals 10. And then in our case, we have the value of h of 17 is 3725. So if we plug in 17 for t, the integral from 9 to 17 of e of x minus d of x, or L of x dx, that's going to be the number of people in the park at t equals 17, which is 3725. For the value for the actual question, they want us to find the value of h prime of 17. So if we take the derivative of this accumulation function, we're just going to get the stuff that's inside the integral. So h prime of t is e of t minus L of t. And then since we want to find h prime of 17, that's e of 17 minus L of 17. Or if you take 17, put it into both of these functions, you'll get negative 380.281. Okay, so that's the value of h prime of 17. And then if we said that h of t is the number of people in the park at a certain time, well, h prime of t then is going to be the rate of change of the amount of people in the park at a certain time. So when we say that h prime of t is this negative number here, we're saying that that is the rate of change of the number of people in the park at t equals 17, namely this value here. So the negative means that it's decreasing. The number of people in the park is decreasing at t equals 17. Okay, now let's look at the final part, D. I keep forgetting to tell you the points. So you'd get 1 point for the numeric calculation, 1 point for an explanation of what h of 17 is, which we did at the beginning of the question, and then another point for h prime of 17's explanation, for a total of 3 points. Alright, part D. At what time for 9 to t is 23, or from 9 is less than or equal to t is less than or equal to 23, does the model predict that the number of people in the park is a maximum? So remember, the number of people in the park at a certain time is given by h of t, like we said in part C. So if we want to find out when the number of people in the park is at a maximum, that's going to be when the derivative is equal to 0, right? So h prime of t, which is the derivative of the number of people in the park at a certain time, is equal to 0. So this is, remember from part C, this is e of t minus L of t. And then on a new line, we're going to say, well, e of t minus L of t is equal to 0. And then if we solve this, I guess you can say e of t equal to L of t. And if you graph this, you will get that t is equal to 17.795 hours after it opens. And notice that this is within the interval 9 to 23, so it is valid. In terms of points, you get 1 point for doing the subtraction and setting it equal to 0, and another point for the final correct answer. That was the question 2. Now let's move on to the third question. Alright, so we have an object moving along the x-axis with initial position. X of 0 is 2. The velocity at time t is greater than 0 is that function given there, sine of pi over 3t. Part A asks, what is the acceleration of the object at time t equals 4? So they want acceleration, we're given velocity, the relationship that should immediately come to your mind is that acceleration is the derivative of velocity, ddt of v of t. So if we evaluate this, that's going to be the derivative with respect to time, of course, of the velocity function, which is given to us in the top as sine of pi over 3 t. See where I got that from? So now that we have this, we can evaluate the derivative. The derivative of sine is cosine, so we'll have cosine of pi over 3t. And then since pi over 3t, this isn't just a t, it's a function with a t in it, we have to take the derivative of this inside function as by the chain rule, giving us an extra pi over 3 that will stick out in the front. Now, we want the acceleration at time t equals 4, so we'll take a of 4, being pi over 3 cosine 4 pi over 3, which is, if you're feeling fancy, in the mood to evaluate trig functions, which you always are, you get pi over 3, nope, you'll get pi over 3 times negative 1/2, which is negative pi over 6. That was a quick one-pointer for the correct numerical evaluation. Alright, so part B. Consider the following two statements. Statement 1, for t between 3 and 4.5, velocity is decreasing. Statement 2, for t between 3 and 4.5, the speed is increasing. Are either or both of these statements correct? Why or why not? Okay, so we need to figure out whether the velocity is decreasing, right? So when is the velocity decreasing? If the velocity is decreasing, then the acceleration is negative, right? So the acceleration is negative. So we want to find out, is the acceleration negative when the acceleration function is between t equals 3 and t equals 4.5? Well, let me write down the acceleration function real quick that we derived in part A. It is equal to pi over 3 cosine of pi over 3 t, like that. And then I want to say, okay, is this negative when t is between 3 and 4.5? Well, to do that, we're going to have to think about quadrants, right? For cosine, the cosine function is negative when it's in the, let's see here, it's in the second and third quadrant. So if we take t equals 3 and plug that in here, cosine is going to be on the x-axis, right? It's going to be cosine of pi, which is negative 1. So if we plug in 3, it's going to be negative. If we plug in 4.5, it's going to be, well, it's going to be on the y-axis now. It's going to be on the negative side of the y-axis. So if we were to, draw our little unit circle here, or draw our thing like that, we're dealing with this section here. So that means our cosine is going to be negative in this third quadrant. Therefore, the acceleration function is going to be negative in the third quadrant. And since we're only dealing with t values in the third quadrant, the acceleration function is going to be negative for all of these t values. So the acceleration function is negative for 3 is less than t is less than 4.5. Therefore, since the acceleration is negative on the time interval, the velocity is also decreasing. Cool. So statement 1, I'll give that a nice red check mark. I like all my check marks to be red. Anyways, statement 2. So for t is between 3 and 4.5, the speed of the object is increasing. What does it mean when the speed is increasing? Let's see. When the speed is increasing, let me erase this stuff here. If the speed is increasing, then the velocity and acceleration have the same sign. That says psi. I don't know, maybe they're sign too. They might be. They have the same sign. So let's look at the velocity function and the acceleration function. Alright, I just wrote that out here real quick. So are these the same sign when t is between 3 and 4.5? Notice that for both of these transcendental functions here, if we put in t equals 3 and t equals 4.5, those are the boundaries for the third quadrant in our circle. That's our third quadrant. And also remember that in this third quadrant, sine and cosine are both negative. So that means the velocity is going to be negative in the third quadrant. The cosine is going to be negative in the third quadrant. Therefore, the velocity and acceleration are both going to be negative in the third quadrant. So since they're both negative, they both have the same sign, that means the speed is increasing. Okay, so statement 2 is also correct. For each statement, provide a reason why it is correct or not correct. So let's see, for statement 1, we'll say statement 1 is correct because the velocity is decreasing, so the acceleration is less than 0 for 3 is less than t is less than 4.5. And then statement 2 is also correct because the acceleration and the velocity have the same sign for 3 is less than t is less than 4.5. So for points, you get 1 point for saying that statement 1 is correct and giving a proper explanation. You're going to get 1 point for just saying that statement 2 is correct, and then a third point for explaining why statement 2 is correct. I guess that's because statement 2 is harder to determine. Alright, let's look at the next part. Okay, so part C. What is the total distance traveled by the object from t equals 0 to t equals 4? So, distance. Do not confuse this for displacement. If you've taken physics, this should be one of the first things that you learn, distance versus displacement. If you don't take physics, know that distance is the integral of speed, while the displacement is the integral of velocity. Okay? So, since we want the distance, we need to take the integral of speed. And remember, speed is the absolute value of velocity. So, since the distance is the integral of the speed, which is the absolute value of the velocity, I'll say that the distance is the integral of the absolute value of the velocity with respect to time, which is the integral from, well, what are our bounds here? We're going from 0 to 4, right? It says there. What is the integral of the absolute value of velocity? Sine of pi over 3t. If you can squeeze that in there. Okay, there we go. dt. And then if this goes in the calculator, we're going to get 2.387, like that. So for points, you get, let's see, you get 1 point for, you get 1 point for including the correct bounds, 0 and 4. You get 1 point for dealing with the fact that distance is not the same thing as displacement. So for including the absolute value signs, basically. And you get a third point for your correct answer. Okay, now let's look at the final part of this question. Okay, so part D, what is the position of the object at time t equals 4? Okay, so if we're doing position, first thing when I think of position, I think of displacement, right? Where displacement is your final position minus your initial position. And I also know that displacement is the integral of velocity. So my displacement is equal to the integral of the velocity function, and the integral from 0 to 4, more specifically, because we're talking about the position at time t equals 4. Alright, so displacement is my final position, my position at the final time, time of 4, minus my initial position, my position at time t equals 0, being this integral. Okay, and then we want to find out what the position is at time t equals 4, so I can solve for this by taking the initial position and moving it to the other side. So x sub 4 is the integral from 0 to 4 of v of t plus x initial. And remember the initial position, they gave it to us up here with the initial position x of 0 is 2. So the time at time t equals 0, the position is 2. So I'll put a 2 in there. And then we know the velocity function, it's given to us here. So you can put this in your calculator, add 2 to it, and you'll get out your final answer of 3.432. Remember, this is the position at time t equals 4. Is that what they wanted, right? That's all they wanted? Yeah, they just wanted the position. This is the 2-point question. 1 point for this integral here, and another point for the correct final answer. Now let's move on to question 4. Okay, so question 4, we have the graph of the function f consisting of 2 line segments shown in the image, and then we have g being the function that's the accumulation function for f, and then in part A we need to find these 3 things of g. Also, there's this note here on the bottom. I don't really know what that means. I'm just going to ignore it and just assume it's not important. Anyway, so A, we need to find g of -1. So I guess that means we should plug in -1 in for x there. So g of -1 is going to be the integral from 0 to -1 of f of t dt. And then notice that how we're going from a bigger number to a smaller number, that's not really, the normal convention. So what we do here is we're going to switch the bounds and just add a negative sign in the front. So you can just put a negative sign in the front here, and then instead of going from 0 to -1, we'll go from -1 to 0. And now this is a more conventional approach, f of t dt. So we're just finding the area from -1 to 0. That's this triangle here. So the area for that is going to be, we're going to have to put the negative sign, and then 1/2 times 1 times 3, which gives -3/2. Okay, and then what's next? G prime of -1. Okay, so first, actually, before we do this, let me just find a general function for g prime of x. Since g of x is equal to this, if I take the derivative of this, I'll have to take the derivative of this. So it's equal to the derivative of this integral of the accumulation function. And when we take the derivative of the accumulation function, we're just going to get out f of x. Right, because the integral and derivative, they're kind of like opposites of each other. So what we said here is that g prime of x equals f of x. So since they wanted us to find g prime of -1, that's going to be equal to f of -1, which, if we look up in the image, is 0. And then finally they wanted us to find g double prime of -1. Okay, so since g prime of x is equal to f of x, g double prime of x is therefore going to be equal to f prime of x, right? Just taking the derivative of both sides. So g double prime of -1 is equal to f prime of -1. And f prime, remember, that's the slope of the tangent line. And since this is the tangent line as well, we can define the slope of this line, and that's going to be the derivative of f. So to find the slope of the line, we'll use 2 points. Let's say, for example, let's use -2, -3, and we'll use 0, 3. So in that case, the slope will be y2 minus y1 over x2 minus x1, which is -6, over -2, which is 3. Okay, and this is a 3-point question, 1 point, 1 point, and 1 point. Okay, so part B, we need to find what values of x in the open interval -2 to 2, so that's this whole interval there, is g increasing. Explain your reasoning. And you'll notice here that I've written that g prime of x is equal to f of x. And when you find some sort of key insight, like we found in part A, such as this, that connects 2 or more main ideas of the problem, I think it's a good idea to write it separately, star it or something, because it's probably going to come back in multiple parts, and you don't want to be stuck figuring out what the connection is when you already found it in a previous part. Okay, so in this case, this is what we're going to use. So they want to find out when g is increasing. So when is g increasing? Well, if g is increasing, then its derivative is positive, right? Since g prime is the same as f of x, this implies that f is positive. So if g is increasing, then f is positive. So we just want to find where on this interval -2 to 2 is f positive. Well, it looks like it's positive from -1 to 1. So since f is positive on -1 to 1, we can go back along here and say that g is increasing on -1 to 1. And they want us to explain your reasoning, and that which means you have to write a sentence saying like g is increasing on -1 is less than x is less than 1 because g prime of x is positive on that interval, right? G prime of x is positive. Okay, part C. This is a pretty similar thing to part B. And if you didn't get part B, I'd try part C because it's a very similar method to what we did in part B. So what you do is you'd have to recognize that if G is concave down, what that means is that G double prime is negative. Okay, and remember how we said that G prime of x is equal to f of x, and G double prime of x is f prime of x? What that would mean is since G double prime of x is negative, since this is true, we can also say that f prime is negative. So where on this graph is f prime negative? What is f prime? F prime is the slope. So when is the slope negative? When is it pointing down? And it looks like on the graph of f, the derivative is negative on this interval here from 0 to 2. That's when it's sloped down like that. So we'd say, well, f prime is negative on 0 to 2, so g is concave down on 0 to 2 as well. For explanation, you can say g is concave down on 0 is less than x is less than 2 because g double prime of x is negative on this interval, or something like that. And for part B and part C, it's 2 points, one for the answer and one for the one for your correct answer and one for your proper explanation. Okay, part D. On the axes provided, sketch a graph of g on the closed interval -2 to 2. Now I realize what this note means. I feel kind of silly, but okay, let's start doing this problem. So we need to sketch a graph of g, right? And the best way I think to sketch a graph is just plug in different points for x and see what we get out for g. So let's make a little table here. We'll have x and we'll have g of x. We'll make a table, we'll plot some points, we'll plot those on the graph and see what shape we get. Okay, let's plug in, I don't know, -2, -1, 0, 1, and 2. Nice easy numbers. They'll get us a good number of points. So I'm going to start with 0 because it's the easiest. If I go from 0 to 0, it's going to be 0. That's because if you take the integral of anything from one number to the same number, it's going to be 0. And then let's see. If we give x equals 1, it's going to be the integral from 0 to 1. So that's this triangle here, which we already said has an area of 3/2. And then for -1, it's this triangle here, which is -3/2, because this is a -1, right? And then for +2, we have this triangle and then this triangle, which are equal in magnitude, opposite in direction. When you add these two up, they're going to cancel each other out and you're going to get 0. And the same logic, oops, no worries, I did that. The same logic is going to apply on this other side. You have this and you have this, equal in magnitude, opposite in direction. They're going to cancel, they're going to come up to 0, right? Now that we've got that, let's start sketching some points, right? Okay, let's see. So 0, 0, it's right there. 1, 3/2. 1, 3/2. Okay, 2, 0, 2, 0. 1, negative 1, -3/2. -1, -3/2. And then -2, 0, -2, 0. So we have it goes down, it goes up, and it goes down. That looks kind of like a sine curve to me. Like that, right? Ish. it's gonna, yeah, something like that. Yeah, okay, that looks good. And so in terms of points, you get 1 point for these 3 zeros there, and then you get 1 point for everything else, like the correct concavity and the correct increasing and decreasing sections, and so on. That's all they want. They just wanted us to draw the graph. Okay, so that was it. Now let's move on to question number 5. A container has the shape of an open right circular cone, as shown in the figure above. The height is 10 centimeters, and the diameter of the opening is also 10 centimeters. That means the radius is 5 centimeters. And that's probably a more useful thing to have. And then we know that the water in the container is evaporating, so at its depth h, it's changing at a constant rate of -3/10 centimeters per hour. Well, this means its depth is changing at -3, so that means the change of the height with respect to time is -3/10 centimeters per hour. That's probably important as well. Right, and then we have the formula for the volume of a cone with height h and radius r. In part A, we're asked to find the volume V of water in the container when h is equal to 5 centimeters. This isn't really a calculus problem, but it's just, a little geometry problem. So, we have that when h is equal to 5, we can just plug h into this equation, but the question is, what's r then? Then you have to realize that the relationship between the height and the radius of this cylindrical or the circular cone. Notice that the height is double the radius. So since the height is double the radius, that that proportion is going to stay the same no matter how high the cone is for this specific cone. So in our case, when the height is 5 centimeters, that's going to be double of the radius. So when the height is 5, the radius is half of that, so it's 5/2. Alright, so now that we got that, we can say, alright, what is the volume? Well, we can just take these two numbers and plug it into the volume equation. So 1/3 times pi times the radius squared times the height. And then the units for this, well, the units for volume are centimeters cubed, since we're dealing with centimeters for our height and our radius and such. So that's the units, and that is the answer. That was a quick 1-point question. Okay, so now in part B, we need to find the rate of change of the volume in the container when h is equal to 5 centimeters. There we go. This seems to be a related rates problem, which really isn't that common on the AP exam, so let's do this. Okay, so when I solve related rates problems, my favorite strategy is to make a list of the stuff that I know and write down what I want to find. So we know that the rate of change of the height is -3/10 centimeters per hour. So I'll write that down again here. dh dt is -3/10. I'm not going to include the units just for keeping it simple. And then I know that the height is going to be 5. So this is the height. And then what else do we know? We know that the radius is going to be half of the height. So it's going to be h/2. And then now that we have this, let's see what we want to find. We want to find the rate of change of the volume. So this is all great and all, but we want the rate of change of the volume, dV dt. So now that we have our list, let's start thinking in terms of equations. What equations do we have? Well, we have two main equations here. We have this equation, and we have this equation. So we know that V is 1/3 pi r squared h, and we can't just take the derivative of this equation immediately because there's two variables here. There's an r, oh dear. There's an r and there's an h. So what we need to do is we need to replace one of these with the other variable. and so therefore we need to find a way to relate the radius and the height. And that's where the other equation comes in, where r is equal to h over 2. So what I'm going to do now is I'm going to make everything in here in terms of h. And the reason I'm doing that is because I know dh dt, so I want to make everything in here in terms of h, so that when I differentiate it, I'll have a known dh dt that I can plug into the equation. If that makes sense. So basically what we're going to do is, since we have an h here, we're going to put everything here in terms of h as well. So what that means is I can take this r and then replace it with h over 2. So this is 1/3 pi h over 2 squared times h. And if I wanted to simplify this a bit, that would be 1/12 pi h cubed. So v is 1/12 pi h cubed. Now that I have this, I can take the derivative of this whole thing with respect to time, of course. So d dt, that's going to give me the derivative of volume with respect to time equals 3. So if I take the derivative of h cubed with the power rule, I'll get 1/4 pi h squared. And then since I have an h here, I can put a dh dt on the end as per the chain rule. Since this isn't a t. Now that I have that, I know my h is 5. I know my dh dt, it's -3/10, and that's why we wanted dh dt, not dr dt, because we didn't have a value for dr dt. I'm not sure if it's the same or not, but since we're explicitly given dh dt, it seemed like the most straightforward way to do it. So since this is what we're solving for dv dt, we'll take dv dt equals 1/4 pi. Well, what's our h? Our h is 5, remember, from our list of known values. So we have a 5 squared, and then our dh dt, that's from our list of known values as well. It's -3/10. So I'll plug in a -3/10 like that, and then you don't need to waste your time evaluating this. This is good enough. And then for our units, because I think they asked for units as well, right? Yeah, they wanted units of measure. We want to find the rate of change of the volume with respect to time. So it's going to be the units for volume divided by the units for time. What's the units for volume? Well, the units for volume are centimeters cubed. And what's the units for time? I think time is in hours? Yeah, it's in hours. So going in hours. So this is the rate of change of the volume with respect to time. Okay, so for points, you get 1 point for stating that r is equal to h over 2. If you instead said this in part A, you get 1 point for that instead of here, but 1 point for stating it in either part A or part B. And then 1 point for rewriting your volume equation in terms of one variable, like we did. You get 2 points for correctly taking the derivative, and then 1 point for plugging in your known values and getting the final answer. Alright, so part C, show that the rate of change of the volume of water in the container due to evaporation is directly proportional to the exposed surface area of the water. So what's exposed surface area of the water? Well, the surface area is this top bit here, right? In this particular scenario, this area here, that's the exposed part of the water. And then if you want to find an equation for that exposed area, that's just the base of the cylinder, right? So if we have a radius r, the exposed surface area, that's just pi r squared, right? If we have a radius r, the surface area is pi r squared. So let me move this down a bit. See? So now we're going to show that the rate of change is directly proportional to the surface area. Okay? So this might seem a little bit confusing because this is an unusual wording for a problem. But since they still want the rate of change of the volume, we'll do exactly the same thing that we did before. We'll just, not have any specific numbers that we're going to plug in. So we'll do the same step as last time. We'll say v is 1/3 pi r squared h. Since r is h over 2, this is equal to 1/12 pi h cubed. Therefore, dv dt is 1/4 pi h squared dh dt. And then since this is always -3/10, this is equal to -3/40 pi h squared. Okay? And then we're not quite done yet. We're almost there. Now, since the surface area is pi r squared, and I want to include an r in this equation, I need to turn this h into an r. So how do I do that? What's the relationship between h and r? So we can substitute something in terms of r for this h. Well, the relationship there is that h is equal to r, or h is equal to 2r, sorry. So since h is equal to 2r, I can replace this h with a 2r. So it's going to be -3/40 pi times 2r squared. And remember, the reason that we're doing this is because we want to relate this to the surface area, which only has an r in it. This is therefore equal to -3/40 times pi times 4r squared. And if I just bring that over there, that's going to be -12/40 times pi r squared. And remember, this pi r squared here, that's the same thing as the surface area of the water. So our findings here is that dv dt is equal to -12/40 times the surface area. Right? So what does that mean? Well, remember how I said that the rate of change of the volume is directly proportional to the surface area of the water? Well, we have, if you've seen like direct proportionality, y is equal to kx, we have something is equal to a proportionality constant times another variable. So they want the constant of proportionality. What's the number that relates these two quantities that are directly related? Well, that's this number here. That's -12/40. So the constant of proportionality is -12/40, like so. So for points, this was a 2-point question. You get 1 point for correctly finding this equation, and then 1 point for stating the constant of proportionality. And then for this whole problem 5 in general, you got 1 extra point if you included correct units everywhere that it was asked for. So parts A and B. And in all honesty, this part C, this was a very tricky and unintuitive sort of thing. I've never seen anything like this anywhere else. So I feel like if you saw this and you didn't know what to do, it's only really worth 2 points. So I feel like the best bet would have been to just skip it and come back. That's just a general test strategy. But if you knew how to do it right off the bat, then by all means, get those 2 points. Let's move on to question number 6. Alright, question 6. So f is a function that's differentiable for all real numbers. There's a table that gives f and its derivatives for selected points from -1.5 to 1.5. And the second derivative has the property that it's greater than 0. So why are they giving us this information that the second derivative is positive on this interval? What does that mean? Well, it means that if the second derivative is positive, then it means that the first derivative is increasing. The first derivative is increasing, and the original function f of x is concave up. Right? They're probably going to ask us for one of these pieces of information sometime in the future. So if we write it down right away, it'll be faster in the long run. We don't have to search for it. So now that we've got that, let's evaluate the integral from 0 to 1.5 of that here. So 0 to 1.5 of 3f prime of x plus 4 dx. Alright, let's just do this integral real quick. So if I do this, I'll get 3 times, well, the integral of f prime of x is just f of x. So this is going to be 3f of x plus, and the integral of 4 is 4x. And we're doing this whole thing from 0 to 1.5, right? And that's equal to 3 f of 1.5 plus 4 times 1.5 minus 3 f of 0 minus 4 times 0, which is 0. So now that I have this, and notice that I still have I have my f of 1.5 and I have my f of 0 here. I don't know how to figure those out. Well, that's why they gave us this table here, right? If we want to know a certain x value, we can just look in the table and we'll figure out f of x and f prime of x. So we have f of 1.5. I can go to x equals 1.5, and I see that f of 1.5 is negative 1. So I'll have, okay, so sorry, we know this is negative 1. And then if you looked at f of 0 on the table, you'd find that f of 0 is, let's see, f of 0 is negative 7. So you'd get that times negative 7, and this is the integral right there. Good. So this was a 2-point question. 1 point for correctly performing the anti-differentiation, and 1 point for the correct answer. Alright, part B. Also, by the way, I just suddenly found a way to make my pen like brighter a little bit. So I don't know if it makes a difference, but hopefully it does. So in part B, we need to write an equation of the tangent line to the graph of f where x equals 1. And we need to use this to approximate a value. So this means we're going to be using a local linear approximation. And then we need to figure out if this approximation is greater than or less than the actual value. So, write an equation to the line tangent. When we're dealing with tangent lines, what I want you to do is you write down on your paper the words point and slope. Okay, because when they give you this, you're going to have to find the point and you're going to find the slope, and you're going to put those together to get your line. So let's see. First, let's figure out the point. What's the point where x equals 1? It's going to be 1 comma f of 1, right? What is f of 1? Well, if we go to our table, when x equals 1, f of 1 is negative 4. So it's 1 comma negative 4, like that. And then slope. What's the slope? Well, the slope is f prime, right? And since we're dealing with the slope at x equals 1, we're going to want to find f prime of 1 to get the slope of the tangent line, which is what the derivative is. So f prime of 1 is going to be, we'll go to x equals 1, we'll go to f prime, and it looks like it's equal to 5. So f prime of 1 is equal to 5. So now we have our point, we have our slope. We can put these together in point-slope form, which, if you don't remember, is y minus y1 is m times x minus x1, where this is our x1 comma y1, and this is our m. So it's going to get us y minus negative 4 is equal to 5 times x minus 1, and that is our tangent line. So if we want to use this to approximate the value of f of 1.2, what that means is I'll just plug in 1.2 in for here and see what y comes out to be. So y minus negative 4 is 5 times 1.2 minus 1. If I solve this for y, that'll give me y is equal to 5 times 0.2 minus 4. So this is my approximation for f of 1.2 using the local linear approximation method by first getting a tangent line and then plugging in the point that I want. Okay, so now we need to figure out, is this approximation greater than or less than the actual value of f of 1.2? Alright, so when we think about overestimation and underestimation, the first thing that should come to your mind is concavity. Alright, so if a function is concave up, like this, and we use a tangent line to approximate it, notice that the approximation is always going to be an underestimate. If we're approximating this value, it's an underestimate. If we're approximating this value, it's an underestimate. But if we're doing this for a function that's concave down, and we draw a tangent line, notice that the tangent line is always an overestimate. If I'm approximating this value, it's an overestimate. If we're approximating this value, it's an overestimate. So if the function is concave up, then it's an underestimate. And if the function is concave down, then it's an overestimate. So the question is our function concave up, where it will be an underestimate, or is it concave down, where it's going to be an overestimate? Well, let's look up in here. Let's look up here and say, look, remember we said in the beginning when we were reading the question for the first time that f of x is concave up? Well, that means we can immediately say, well, okay, it's concave up, so it's an underestimate. Boom, we're done. If we didn't know that, we would have had to go search around the question and find this again. So we save some time in the beginning. And so we'll say, well, the approximation is an underestimate because f of x is concave up on 1 is less than x is less than 1.2. And I said 1 and 1.2 because we're dealing with x equals 1 and x equals 1.2. Those are the only values we care about, really. So, yeah. And for points, this is a 3-point question. 1, 2, and then the third point for saying that it's an underestimate with a proper explanation. Alright, part C. Find a positive real number r having the property that there must exist a value c where c is between 0 and 0.5 and f double prime of c equals r. So when I see something like this, the first thing that comes to my mind is either the mean value theorem or the intermediate value theorem. And in this case, we're going to be using the mean value theorem, okay? Because we have f double prime. So if we want to do this out, we'll say, okay, so by the mean value theorem, we know that there must exist a value of c between 0 and 0.5, where this is equal to the average rate of change of f prime, where f double prime is equal to the average rate of change of f prime on 0 and 0.5, right? So f double prime of c is equal to the average rate of change of f prime. So that's f prime of 0.5 minus f prime of 0 over 0.5 minus 0. Remember, that's what the mean value theorem says. It says that the derivative is equal to the average rate of change on the interval at some point, if the function, meets the requirements. So what is this equal to? Well, we're going to look up on our table. F prime of 0.5, 3, minus f prime of 0, 0, 0, like that, over 0.5, which is equal to 6. So that's f double prime of c. And then remember, they said f double prime of c is equal to r, and we want to find that number r, right? We said f double prime of c equals some number r, which is 6. So therefore r equals 6. Alright, is that all they wanted? Yes, they wanted a reason for the answer. So we'll say, by the mean value theorem, there exists a number c such that 0 is less than c is less than 0.5, and this stuff is true. Okay, that was just that was a 2-point question. 1 point for getting the right answer for r, and another point for an explanation involving the mean value theorem. Part D. So let g be the function given by that stuff. The graph of g passes through each of the points x comma f of x given in this table above. So this applies to f and for g. So is it possible then that f and g are the same function? Honestly, when I looked at this question for the first time, I had absolutely no idea what to do here, because it's so unlike anything I've seen before. But one way we can do it is that there's multiple ways you could approach this problem. The one that seems simplest to me after thinking about it for a bit is that, okay, so we know that if we look at g of x, so for x is greater than or equal to 0, we know that for g of x, if we take the second derivative of g of x, just by taking the second derivative of this function, it's going to be equal to 4, right? However, remember how in part C we said that there's some value c such that f double prime of c is equal to 6. So we said that f prime of c is equal to 6 for some c is greater than 0. Well, these are conflicting pieces of evidence, right? Here it says that the second derivative is 4 for x is greater than 0, but here it says that the second derivative is 6 at some point where x is greater than 0. So since the second derivatives are different, then these two both can't be the same function. And for the explanation, I'd probably write something like, we know that f double prime of c is 6 for some c is greater than or equal to 0, but g double prime of x is 4 for x is greater than 0. Therefore, f of x and g of x are not the same function. Okay, and this was a 2-point question. So 1 point for a correct explanation and 1 point for a correct answer. Alright, so that's the culmination of the 2002 AP Calculus AB exam review video. I hope you found this helpful, and I will see you next time. Goodbye.